Hello everyone, and thank you for joining our webinar. A few housekeeping reminders before we begin today. You all have joined in on mute, and during any time of the presentation, if you have questions, please feel free to post it on the chat window. We will address all the questions at the end of the webinar. Let me begin by introducing myself. My name is Devangana Mukherjee. I'm the Director of Business Development and Sales at CISC Semiconductor. I've been working in the RFID industry for the last 5 years. I'm currently the member of board in AIM North America and also have worked in different work groups in RAIN RFID Alliance. I'm currently the co-chair of the aviation work group in RAIN RFID Alliance. My co-presenter today is Dr. Wojtek Derbek. He's the head of R&D for CISC Semiconductor. He has been working in the RFID industry for the last 14 years and overlooks the development of RFID testing equipments and standards globally. He is an advisor to the RAIN Technical Work Group and is also the co-chair of GS1 EPC Global Performance Work. Now a little bit about the company. CISC Semiconductor was founded in 1999 and is a leading supplier of RFID test equipments and solutions globally. We are a 100% privately owned company headquartered in Klagenfurt, Austria, with R&D offices in Graz and in Klagenfurt. We also have a sales office in Mountain View, California. We are proud to serve customers globally, and our test equipments are being used in different verticals such as retail, asset tracking, healthcare, aviation, tire tracking, to name a few. We pride ourselves to be managed by an international team of highly skilled experts working in the NFC and RFID industry for more than 20 years. CISC is a team of RFID NFC professionals with long-term commitment towards improving the products and systems through our measurement tool solutions. So we look into NFC and RFID conformance, performance, and interoperability tests. Now let us look into some of the challenges in the current RFID market. 2017 was a great year for RAIN RFID technology. The technology that started out as a solution to improve inventory management in logistics was now being used in different verticals. Some of its applications include tracking vital drugs in hospitals, timing races, tracking bags in airline industry, workflow management in industrial manufacturing, or simply enhancing a customer experience in a changing room in retail. The demand is manifold. However, this was not possible earlier. Historically, the RAIN RFID tags had short read ranges. This, along with the power demand of the tag, were the main limiting factors to see how the performance of a RAIN reader would be at the point of deployment. In current generation tags, however, as the tags have become more sensitive, the return link of the tag has become the main factors to understand the sensitivity of the reader. But when you use the term sensitivity of a RAIN reader, what do you mean? There is a gap in understanding the term sensitivity of the RAIN readers. There are a number of factors that affect the performance of the readers. Some of them being the transmit power of the reader, the phase of the tag signal that is received by the reader, the frequency at which the reader operates. All of these affect the final sensitivity of the RAIN reader. Therefore, before choosing a reader for your application, it is vital that these readers are properly evaluated at the R&D phase. You need to look into how the performance of these readers are, considering considering some of the tag parameters. We need to look into the backlink frequency of the tag, how the reader reacts when the tari value changes. We need to see how the reader reacts when the transmit power of the reader changes. We also need to look into system parameters while evaluating a RAIN reader for an application. We need to see how the sensitivity or the performance of the reader changes in the different phase signals of the tag. In today's environment, what is also required is a 100% read range. Typically, RAIN readers are required to read multiple tags with very low return power, return links in varying noise environments. Hence, there are high chances of misreads and duplicate reads by the reader. We need to make sure that the software being used is fine-tuned and keep a close eye into the communication package between the tag and the reader. These are some of the factors that are making RFID deployment challenging in today's environment. The main aim of the webinar today is to discuss some of these factors, to look into what is affecting the sensitivity of the RAIN readers, what to expect during the process of evaluation, and how can we troubleshoot and eliminate these challenges. The next part of the presentation would be presented by Wojtek, and he would begin by talking about the factors affecting the sensitivity of the RAIN reader.
So the reader sensitivity will be a result of both the design choices in the reader electronics as well as the signal interpretation software. These will cover the signal amplification, filtering, and other functionality that affect the reader sensitivity. It's worth noting that the reader sensitivity does not depend on the RF environment. So for instance, it does not change if the number of RFID tags or readers changes, or if there is an additional RF interference. So the RF environment will affect the system performance, but it will do so via the signal quality and the propagation effects, and not by changing the receiver sensitivity. So if we take a look at the design factors that have the most significant influence on the sensitivity of a reader, it is the reader transmit power, which causes self-jamming. Many users are aware of the fact that the higher the transmit power, the lower the sensitivity typically, but we can take a look at the details of how valid this statement is later on. Then also the tolerance of the to the imperfections of tags is an important aspect for the sensitivity of readers. Here, the most significant parameter is the offset of the backlink frequency. We are aware that the UHF RFID system is a non-synchronous system. The tag has its own clock signal, its own oscillator, and the actual backlink frequency that is sent by the tag might be different from the backlink frequency that is requested from the reader. So there is a small misalignment, or might be a small misalignment between what the reader expects and what it gets from the tag. So that's on this topic. And the third thing is also the impact of the phase of the received signal on the sensitivity of the reader due to the IQ imbalance and other factors of the reader design. Now, we should take a look at how the sensitivity of a reader is designed. It's the lowest level of the received signal to achieve an intended read success rate. And here the key metric to measure the sensitivity is the backscatter power of the tag at the receive port of the reader or at the antenna of the reader. So one of the interesting dependencies or plots that we can do to evaluate the reader sensitivity is the dependency of the read success rate over the received signal at the reader. And we see that if the tag signal is strong, the reader will have a good read rate. On the other hand, the lower the tag signal, the worse the success rate. That means receiving the tag answers. So a reader will, in this case, correctly interpret 1% of tag messages when the signal at the receiver, the tag signal at the receiver, has strength, in this case, minus 74 dBm. But the same reader will correctly interpret 90% of messages when the signal is a bit stronger, in this case minus 68 dBm. And there is this 90% read success rate criteria, which is set by default by the RAIN RFID reader sensitivity test protocol or guideline, which is used to evaluate the reader sensitivity. Now, few words about how reader sensitivity is measured. We at CISC provide the tool RFID Explorer, which is a tool for measurement both the tags and readers, both performance and conformance, to analyze the communication between readers and tags and analyze RF signals in general. We provide 4 main test modes in this device, which is the sniffer and protocol analyzer, which is used to observe and analyze the communication between tags and readers. Then the tag emulator, which is actually the core system to measure the sensitivity of readers. Then the field recorder, and actually for testing of the RFID readers, the sensitivity measurement software. Now, tests can be done in 2 ways. Either contacted testing, where the reader is connected to the test unit over a short cable and an attenuator to measure the sensitivity, or a contactless testing, where the reader has either a built-in antenna or you would like to measure the reader including the antenna. So in this case, we provide an RF sensor module which can measure the sensitivity of a reader over the air, just as shown in this picture. This is the reader and this is the RF sensor module and the measurement at a fixed distance. Now, I would like to show the 3 sensitivity measurement cases that I mentioned previously. That means the power dependent sensitivity. This is what I would like to start with. As I said, typically the higher the transmit power, the lower the sensitivity. In this plot, we see the dependency of the sensitivity here on the vertical axis on the transmit power. And this is a typical result for standard readers. Low sensitivity at high transmit power, better sensitivity at low transmit powers. There is less known aspect, which is the phase dependent sensitivity. So depending on the phase at which the tag answer arrives at the receiver of the reader, we will observe with some readers, not with all readers, but with some readers, we will observe a variation in the sensitivity. In an application setup, the phase varies in dependency of the distance between the reader and the tag. So virtually the signal can arrive either in the I or the Q channel or partly in the RI or in the Q channel. And if the sensitivity in the I or in the Q channel is lower, then we would see this variation. So in this particular example, we have a reader 1, which has a very strong sensitivity variation due to the phase of the received signal. On the horizontal axis, we see the phase from 0 to 360 degrees, and on the vertical axis, the sensitivity. You see that the variation is approximately 14 or 13 dB, which is a lot. On the other hand, there are other readers which do not suffer from this phase-dependent sensitivity, like the reader 2, 3, 4, 5. Actually, for the reader number 3, there is a slight dependence of the sensitivity, but this reader has a very good sensitivity in general, and this variation is not more than 3 dB, say. So this is one of the less known things. And then there is also the sensitivity is also dependent on other factors like the backscatter link frequency. As I said, the tag can answer with a backlink frequency which will be slightly different from what the reader expects due to its internal oscillator. Miss oscillator frequency difference or inaccuracy, say. Here I'm showing a result of a sensitivity measurement of a reader where the target backlink frequency was 256 kilohertz. And then using the test tool, we were shifting the backlink frequency, intentionally shifting the backlink frequency of the tag answer to higher frequencies or to lower frequencies to see how much the reader sensitivity changes independently of this parameter. And here we see that the more away we are from the target frequency, the lower the sensitivity. But the variation is not that significant. We see 1.5 dB variation over this band that we have tested. So this reader, I would say, performs very well in terms of the backlink frequency stability. There are other readers which can have a higher dependency on the backlink frequency mismatch, say. Here, the target frequency BLF requested by the reader was 320 kilohertz. And if the tag answers with, say, 280 kilohertz, which would be about 15% off from the target frequency, the received sensitivity would change by approximately 4 dB. And of course, the RFID protocol allows some variation of the backlink frequency. The variation depends actually on the backlink frequency itself, the allowed variation. And it can be between 6% and up to 20%. So this is a factor that has to be considered in the sensitivity measurements. Now, I would like to discuss a bit more into a detail of the test method, how the sensitivity is measured. Either you can use a reference tag or a tag emulator. The advantage of using a tag emulator is that a user or a test unit has the ability to control the tag behavior. The tag emulator reports its internal states, received commands of the reader, and this is used to control and speed up the test flow. So in our tools, we are using a tag emulator. The test sequence, which is used for the testing, is the query. The tag emulator responds with RN16, then the reader sends an ECC command, and the tag sends the PC, and CRC. And then what we want to know is whether the reader understood the tag answers or not. So from the sequence, we can evaluate this. So we can also take a look at the RECRN command, which would be more or less a confirmation that the reader received correctly the EPC of the tag. So there are two definitions of the read success rates. Either some readers, they send so-called fast inventory, where they do not continue after receiving the EPC of the tag. They do not continue with sending the RECRN command, or the readers do that. So depending on whether we can get the RECRN from the reader or not, we are able to either check that the EPC was received by the reader, or we are able only to verify that the RN16 was received by the reader. And this makes the difference in the definitions of the success rates. The success rate for consistency shall be based on at least 100 read cycles to maintain some good statistical data for the sensitivity. Now, depending on whether the user, whether the reader sends the fast inventory or the full inventory using the RN16, we have measured the sensitivity in these two modes, and just to see how much difference we see in the measured sensitivity if we take a look at the RN16 only, or if we measure the success rate of the EPC. And what we see is that there is a certain variation or difference, which in this case is approximately up to 6 dB. So the measurement method, which takes a look at the EPC response of the tag, or the ability of the reader to understand the EPC, is more accurate, and at the same time it reports slightly worse sensitivity, which is a natural effect than the method which is taking a look at just receiving the RN16 of the tag. Now, so that was on the general topics, and I would like to move on to the variation to discussing or showing results of reader sensitivity measurements. The same reader can report different sensitivity, not just because of the parameters that we have analyzed before, but also due to some other aspects like the configuration and software settings. So we have observed in the measurements that we have done in our evaluations that depending on what the backlink frequency is, depending on what the backlink frequency is used, there is an additional variation in the sensitivity. Also, the reader sensitivity is dependent on the carrier frequency. So now let's take a look at the results. First of all, this is the evaluation of the sensitivity at different backlink frequencies and different coding used by the reader. So this is one reader which was measured for the backlink frequency ranging from 40 kilohertz through 640 kilohertz. We see that the sensitivity of the reader shows this behavior, typical behavior, that the higher the transmit power, the lower the sensitivity. And it is more or less independent on the backlink frequency. So these different lines show different backlink frequencies requested by the reader. And the results are within 2 dB. So this is very consistent. However, if the backlink frequency was 640 kilohertz, the reader sensitivity was much more different from, actually it was worse than for the other BLFs. And important is also to know, to mention that this backlink frequency was requested by the reader, whereas previously we were looking at the variation of the backlink frequency due to the inaccuracy of the oscillator of the tag. So these are two different measurements. Second test was to see the stability of the frequency over stability of the sensitivity over different frequencies. And here again, we see the dependency of the sensitivity on the transmit power. Here, the blue plot is the measurement of the reader which was operating at a single frequency, single carrier frequency, 915 megahertz. The red plot was obtained for the measurement during the frequency hopping of the reader, and the variation is 3 dB in this particular case, up to 3 dB, which shows that during the frequency hopping, there were probably some frequencies at which the sensitivity was lower, and therefore the overall result is worse. If we want to go into more detail to see how why this happens, we can always take a look at the success rate plot, which displays the dependency of the success rate. That means the percentage of the successfully read tag answers over the strength of the tag answer at the receiver of the reader. So here we see that if the tag answer is strong, there is 100% success rate or 98%. At a certain point, when the backscatter power of the tag gets weaker, and here actually the measurement is done in a way that we vary the backscatter power of the tag emulator during the measurement. The reader stops or decreases its success rates. It misses some tag answers, and again, this was frequency hopping. So at the point when the tag emulator was actually measuring, or it was sending a tag answer at minus 83 dBm, the measurement was done probably at a different frequency than when the tag emulator was measuring in the next step at minus 84 dBm. So this is the reason why we see these spikes here in the plot. So, and depending on how we define the sensitivity based on the success rate plot, we see the variation of 5 dB, or depending on, in other words, depending on which frequency the reader operates, we can see the variation of the sensitivity of up to 5 dB here on the horizontal axis. There was another reader, reader C here, which, however, had almost no dependency of the sensitivity on the carrier frequency. We can see it from the success rate plot. The upper picture was taken for the case when the reader was operating on a single frequency. We see it was that the reader had a 100% success rate until the signal of the tag at the receiver was minus 73 dBm, and then the success rate dropped down. And when the reader was hopping, frequency hopping, the shape of the plot did not change. So that was another reader which performed significantly different from the reader B, which I showed in the previous slide. Now, we have also seen that depending on some sets of parameters that you configure with the reader software that comes from the reader manufacturer, you can obtain different sensitivity, and we wanted to understand why that is. So reader manufacturers, they provide sets of parameters or even different softwares for different modes of the operation of their readers. So we have taken these parameters and the different softwares for a single reader in this case and evaluated the sensitivity. And we had the configuration set number 1, number 2, and number 3. They differed in backlink frequency and in some other parameters, and in a way how the reader operates in general. And we could see that the same reader had a very strong variation of the sensitivity depending on how it is configured, which is an important thing that shows that a good reader sensitivity can be achieved with the reader with some set of parameters. However, if other parameters are used, the same reader could perform much worse in this case. And the variation that we see here is approximately 20 dB, which is a lot. Now, if we want to understand more about how these parameters, where is the difference actually in these parameters of the reader, we provide a tool which is called CISC RFID Explorer Sniffer, which lets you analyze the communication between the reader and tags, and it displays all the communication in this form of signals, analyzes the commands, their parameters, and gives you an overview of what the reader does in detail. It features the real-time recording functionality of the communication between the reader and the tag. And all the communication can be actually recorded on the hard drive and analyzed even later on for more details. The typical result of the analysis is for every pair of the command and the tag answer, the description of what the command is, what the content is, and how the tag answered. Also the timing parameters for every command, and the link timing, and so on. So there is lots of functions behind this CISC RFID Explorer Sniffer, which helps to analyze the behavior of the software, of the reader. Now, finally, I would like to demonstrate how a reader sensitivity is measured. I have connected a reader under test over a cable and an attenuator to the test unit, which in this case is the RF sensor module. And the sensor module is connected to the CISC RFID Explorer. And I will now show how the measurement is done. So first thing that needs to be done is actually to configure the reader under test, to set the transmit power, and to check the parameters of the reader to be as expected. I can now start the reader to read the tags using the reader application, and I have switched now to the CISC RFID Explorer reader performance software to start the measurement. So I have to enter a few things like the carrier frequency at which the reader operates. I have connected the reader over the cable and the 26 dB attenuator to the test unit. So this is what I need to enter here in the software. Press OK, and the measurement will now start. The test unit is sweeping the backscatter power, and now the first measurement comes, which shows that the reader was sending 27.5 dBm transmit power, and the sensitivity was -50 dBm. I can also see that the parameters of the reader commands and of the use tag answer, the BLF of the tag answer was 256 kilohertz. And now I would like to know how the reader performs, what the sensitivity is if I change the transmit power of the reader. So I'm switching back actually to the application of the reader to set a different output power, starting the reading of the reader, and I will continue the measurement by pressing the continue plot. So again, the test unit is changing the backscatter power of the tag answer to see at which level the reader operates with 90% read success rate, and this plots the sensitivity, which in this case is minus 58 dBm. And so if we compare it to the previously measured point, minus 50 dBm, we see that the sensitivity improved. And that was just because we have decreased the transmit power. So I will now set the reader, again using the reader application that comes from the manufacturer, to a third different power level to get a third measurement point. And continue the measurement. I will get a third point in my plot that will show that the reader was now transmitting 19 dBm transmit power, and the reader sensitivity was minus 58 dBm, so same as in the previous measurement point where the transmit power was 25 dBm. So sensitivity didn't change anymore with further decreasing of the tag power, reader power. Now we should take a look at the success rate plot to understand the result. So we see that if the power of the tag answer was minus 56 dBm, the success rate of receiving the tag answer was 100% on the reader side. But the lower the backscatter power of the tag, that means the lower the signal at the receiver, the lower the success rate. And at a certain point, we have crossed this 90% success rate criteria, which defines the point at which the sensitivity is measured. So the minus 57.5 dBm is the measurement point, which is then plotted on the screen that we were looking at before. And we see that if the tag answer is minus 67 dBm, the reader doesn't read the tag at all. If the answer is minus 60 dBm, there is only 20% success rate. Now, we can also take a look at the received signal to see what the reader, how the reader communicates with the tag. So we see that the sequence was the query command sent by the reader. The tag emulator answered with the RN16. Then the reader sent the ECC command, and the tag replied with the PC, EPC, and CRC. And we can zoom into the plot to see the signals in detail. Now, this is the typical behavior of the reader. The higher the transmit power, the lower the sensitivity. But at a certain point, the sensitivity stays constant, and it doesn't improve any longer with further degradation of the, or decreasing the transmit power of the reader. So we can call the plot reader 1, save the data in a text file for further processing to work with the data later on. Good, so that's the demonstration. Now, Debs, I would like to hand over back to you.
Thank you so much, Wojtek. Hopefully we have been able to clarify some of the questions around testing the sensitivity of a reader and also understand the term better. If there are any questions regarding the presentation, please feel free to leave the question in the chat box. We would be happy to answer any questions that you may have at this point. Wojtek, one of the questions that I have received is there a special software to control the reader? So do I need a special application interface to connect the reader and have it tested?
The answer is no. There is no special requirement, no special interface required for the reader. So you take the reader that you want to test as it is, including the software that comes from the reader manufacturer. In the software, you do the configuration, and the measurement software runs in parallel. And actually, the measurement of the transmit power, as well as the strength of the signal at the receiver of the reader, this is all handled by the CISC test software by Explorer, so the user doesn't have to use any power meter to do measurements. The system is fully calibrated and automated.
Yet another question that has come is, you recommended measuring the sensitivity of a reader with the help of a tag emulator. Why do you recommend a tag emulator over a normal tag?
Now, we have seen in the presentation that the sensitivity of the reader depends on various factors. One of them was, for instance, the backlink frequency or the phase of the signal that comes to the receiver. So with the help of the tag emulator, we are able to control the behavior of the tag to set the backlink frequency. This is something that you cannot do with a standard tag that you could use otherwise to do simple measurement. In addition, you do not have to perform any calibration steps because the software and the system comes calibrated. So that's the advantage of using the tag emulator.
Thank you. So these are the two questions that I had received from our listeners today. If there are no further questions, I would slowly conclude the webinar for today. Thank you everyone for joining the webinar. I would be sending the link to download the slides shortly. And at any given point, if there's still questions around our presentation, please feel free to get back to either Wojtek or me regarding this webinar. Thank you so much. Bye-bye.
Thank you. Goodbye.